Hello guys, this is a video solution for the problem sheet for week 2. There are 14 questions on this problem sheet. I will go through every single one of them and give you a detailed solution. Please note that this video solution is on top of the typed solution and the handwritten solutions. Question 1 is to find the density functions, in other words the PDFs of the following: of the Gumpel CDF, which is denoted by this, and the Fresher CDF, which is denoted by this, and the Viable CDF, which is denoted by this. Okay. Alright, so I'll start with remember the Gumpel CDF is given by this formula here, you may recall. Okay. X from minus to plus infinity. Now you should differentiate this with respect to x, right? You will get the following. Alright, and the Fresher CDF is given by this. Alright. Now you should differentiate this with respect to x. You will get the following. And finally the Viable CDF is given by this. Okay. Now, so you should differentiate this with respect to x. You will get the following. All right. So that completes question 1 of sheet 1, and the second question, sheet 1, is to find the mean corresponding to the 3 limits. So number 2, the mean, find the means corresponding to the 3 limiting distributions: the Gumpel, the Fresher, and the Viable. Right? So I'll start with the Gumpel, right? So to find the mean, I'm sure all of you know, you just need to integrate x times the density function, which we already worked out. right? And the limits of integration are from minus to plus infinity dx. Okay. To do this integration, you need substitution. I mean, you learn substitution by experience. So in this case, an obvious substitution is to set y equal to this. So x becomes minus log of y, and dx by dy becomes minus 1 over y. Right, so let's put this in a box. Alright, so the integral becomes, now the limits of integration, when x is minus infinity, y is plus infinity, and when x is plus infinity, y is 0. Okay, so you get right. Now you see the y here cancels out with the y here, right? And I'm going to use the minus sign here to switch the limits from infinity to 0 to 0 to infinity, right? And I'm going to pull the minus outside, so there's a minus outside. So log of y e of minus y dy. Okay. Now this is where I'm going to use a trick that a trick which is a differentiation trick, which is on the course website. I did a video on that, you may recall. The trick says the following, that if you have right, this here is equal to log of y. I mean, if you don't remember this, please look at the course website. There's a video explaining this trick in the course website, right? So you can replace this guy here by this. That's what it says. So this becomes minus 0 to infinity okay. So this becomes, I'm going to take the derivative operation outside the integral. Right. Okay. Now this, you may recall, is the definition of a gamma function. Again, there's a video on the gamma function which you can find on the course website. So by definition, this is a gamma function at a plus 1, right? All right, so this becomes minus the derivative of the gamma function at a plus 1 at a equal to 0, so it is 1. So this is the answer to the mean of the Gumbel distribution. So it's the derivative of the gamma function at 1. Okay. Right. So that's just only the first part of question 2. The second part is to find the mean for the Fréchet distribution, right? So the mean for the Fréchet is going to be the integral. This time the limits of integration are from 0 to infinity, so it's 0 to infinity of x times the density, which is alpha, excuse me, alpha x power minus alpha minus 1 e dx. Right. So alpha is a constant, so you can pull it outside, so this becomes 0 to infinity of so here I'm going to make the following substitution. Y equal to is equal to this, right? So x will be so dx by dy is this. Alright, so let me put this in the box. Okay. So if you substitute this into the integrand, you will get this. Right, when x is 0, y is infinity. When x is infinity, y is 0. So the limits will go from infinity to 0. Y okay. Now I'm going to use the minus sign here to change the limits infinity to 0 to infinity, and the alpha, you see the two alphas cancel out, and also the y you can multiply with this, so you'll get the following: 0 to infinity of y okay, and this again is a gamma function. This time is a gamma function at 1 minus 1 over alpha. So this is the mean of the Frechet distribution, right? And the third part of question 2 is to find the mean of the variable. Right, so this is going to be the integral because the variable is defined on the negative axis, real axis. The integral is from minus infinity to 0 of x times the density function, which is alpha minus x power alpha minus 1 e minus x power alpha dx, right? Okay, let's take the alpha outside, so this is going to be alpha, and let's also take the okay, let's keep the minus inside, so this becomes minus infinity to 0 of x times okay. Now at this stage I'm going to make a substitution, and here I'm going to choose to substitute for minus x power alpha, right? Okay, so this implies that x will be equal to minus of this, right? So dx by dy will be minus Okay. So let me put this in a box. Okay. Now let's do the substitution. So you get alpha. The limits of integration, when x is minus infinity, this becomes plus infinity, right? When x is 0, is 0, right? And x you can replace by this, all right? And this guy here you can replace like this. Right, and this becomes this, and dx by dy is okay. So you see a few things cancel out, including the alpha. And once again, I'm going to use the minus sign here to change the limits around. So it's going to be 0 to infinity. I'm going to pull this negative outside, right? So you get, after some simplification, this is what you will get, I think. Okay, hope I'm correct. All right, now once again, using the definition of the gamma function, what you have here is the gamma function at 1 plus 1 over alpha. Right, so this is the mean for the Weibull distribution, right? Okay, so this completes question 2 of sheet 1. The next question number 3. Question number 3 is to find the variances corresponding to the 3 limits. Right? So this is 3. Find corresponding to the Gumbel distribution, the Frechet distribution, and the Weibull distribution, right? So we already know the mean. So to find the variance, we need to simply let's start with the Gumbel. So to find the variance for the Gumbel, you need to just simply integrate from minus to plus infinity minus of x squared times the density function. Which is this, right? So this will give you the expectation of x squared. Then from this you will subtract the mean, which you already got. You may recall it is equal to this. This is what we got for the mean. So you need to square this, right? Okay. Now to do this integration, once again I'm going to make the same substitution that I made to find the mean, right? Okay, which was this one. So this implies that x equals to minus log of y. Okay, so dx by dy is minus 1 over y. All right, let me put this in a box. Okay, so making the substitution, this is the limits of integration as before will go from infinity to 0. X squared will become and then you have the square of the mean, which is this. Right, now I'm going to use the negative sign here to switch the limits around, so you get the y and the y cancel, so you get log of the integral of log of y squared e of minus y dy minus right. Now I'm going to use the same differentiation trick that I mentioned before in question 2. Now this, the trick this time is slightly different. Again, please look at the course website. You will see what I'm doing. All right, this is the trick I'm going to use this time. All right. Okay. So basically, you can replace the square of log of y by the second derivative of y to the power a at a equal to 0. Right. So this becomes right. Now I'm going to take the derivative operation outside the integral, so it becomes right. Now what you have here is once again the gamma function at a plus 1, right? So this is okay. So the final answer is the second derivative of the gamma function worked out at a plus 1, but a equal to 0, so it gives you 1, right, minus okay. So this is the formula for the variance of the Gumbel limit. Okay. Now we will find the variance for the fresh air distribution. So it's going to be the integral from 0 to infinity of x squared times the density function for fresh air, which we worked out earlier in question 1, dx minus the square of the mean, which is, we worked out the mean for fresh air in question 2. So this is the mean. Alright, this can be written as follows: alpha times the integral from 0 to infinity of x power 1 minus alpha Alright, now I'm going to make a substitution. So in this case, an obvious substitution is to set y equal to this. So x will be equal to y power minus 1 over alpha, and dx by dy will be this. Alright, now let me put this in a box. Now substituting everything inside the box to the integrand, this is what you will get. You will get alpha. The limits will change. When x is 0, y will be infinity. When y is 0, x is 0, y will be x is infinity, y will be 0. Right? So you will get the following. Alright. Now I'm going to use this negative sign here to switch the limits from infinity to 0 to infinity, right? And the alpha here will cancel with the alpha here. Sorry, I forgot to subtract. I forgot to subtract the mean. Okay, these two alphas will cancel, and few other things will also simplify. So you will get the following. The integral from 0 to infinity of y minus power minus 2 over alpha. Okay, then minus the square of the mean. Right. Now this is obviously a gamma function from the definition of a gamma function. I did a video on gamma function which is on the course website, so please have a look. So by definition of a gamma function, this is equal to this, and minus the square of the mean. So this is the variance. This is the variance for the threshold distribution. Variance for the Weibull limit, right, it's going to be minus infinity to 0 of x squared times the density function, which is this. Okay, minus the square of the mean, which is this. Right. Alpha is a constant. You can pull outside. These two you can combine. So this becomes alpha times minus x power alpha plus 1 . Okay. Alright, I'm going to make the same substitution I made earlier. So I'm going to set this, right? So which implies that x is equal to minus, so dx by dy okay. Now let me put this in a box. Alright, making the substitution, you get alpha. The limits of integration will change to infinity to 0, and this guy here will become the following. Then you get this, and dx by dy is okay. This is what you get, and you have to subtract. Don't forget to subtract the square of the mean. Okay. Now I'm going to use the minus sign here to switch the limits. The alpha and the alpha will cancel, so you get 0 to infinity of okay, minus the square of the mean. Okay, now again using the definition of the gamma function, what you have is here is equal to gamma function at 1 plus 2 divided by alpha minus the square of the mean. So this is the variance for the viable limit. Okay. So this completes question 3 of sheet 1. Right. Okay. The next question is question 4. So question 4 is to show that, okay, question 4 is to find an equivalent condition, if and only if condition, for the following. Okay, where this obviously denotes the Gumbel limit. Okay. So this is equivalent to saying that, let's put in the formula for the Gumbel, which is E minus E x. Right. Okay. All right, and this is equivalent to saying that, okay, this power n is equal to all right, now let's take the log both sides. So I'm going to take the log on the left and the right hand side. So you get minus right? The two minuses cancel out, so you get n times e minus x equal to e right. Now I'm going to take logs one more time, right, on the left and the right hand side. So log of this is log of n minus x, and log of this is minus alpha n x minus beta n. Alright, now I'm going to equate the coefficients. So I'm going to equate the constants on the left and the constant on the right. And I'm also going to equate the coefficient of x on the left and the coefficient of x on the right. All right, the constant on the left-hand side is log of n. And the constant on the right-hand side is minus beta n. And the coefficient of x on the left-hand side is minus 1. And the coefficient of x on the right-hand side is minus alpha n. So what you have is the following. You have beta n equal to minus log of n, and alpha n equal to 1. So that proves question number 4. Right? Which hope you get this. All right. Now question 5 is similar. So let me show you how to do that. So this is question number 5. So here we start with the following statement. Power n equal to this is n, alpha, that's right, alpha nx plus beta n, So this is equivalent to, I'm sure all of you know the formula for the Fréchet limit, which is so this okay. Now the left hand side is simply equal to E Now I'm going to take the logs, the left and the right. Okay, so the log of the left is minus this here, and the log of the right hand side is okay. And then I'm going to cancel out the two negative signs, so it becomes okay. All right, in the next step I'm going to take the power of minus 1 over alpha on both sides. So whatever you have on the left hand side, I'm going to power this to this, and the same thing on the right hand side. Okay, so this guy here becomes n to the power minus 1 over alpha times x, and the right hand side becomes this. Alright, now the same as before, I'm going to equate the coefficients of x on both sides and the constants on both sides. Alright, starting with the constant on the left hand side is 0. The constant on the right hand side is beta n. The coefficient of x on the left is this, and the coefficient of x on the right is this. Alright, so hence we have shown that the equivalent condition is that the beta n is 0 and the alpha n is this. Alright, so that completes question number 5 of sheet 1. And question number 6 is similar. Here we are. So here we start with the following. We have the variable limit, right, power n equal to okay. Now this is equivalent to saying, I'm sure you guys remember the variable limit, which is e minus alpha over n okay. Right, now this power n is equal to this, and this is the same as right. Now, as before, I'm going to take the log both sides. So you get minus n okay. This after taking the logs. Alright, now I'm going to cancel out the two negative signs. Right? So you get n right. Next I'm going to take the power 1 over alpha both sides, right. If you do that, you get on the left hand side you will get the following. And on the right hand side you get this, right? The minus here and the minus here goes, so this becomes right. Now Okay, equating the constants on the left, the constant on the left hand side is 0, the constant on the right hand side is this. The coefficient of x on the left hand side is this, and the coefficient of x on the right is this. So we have proved that beta n is 0 and alpha n is this. All right, so we have proved question 6. Okay. All right. The next question on sheet 1 is question 7. Right. The question is to find all right, this is, I'm sure all of you know, this is the exponential distribution. So we want to find which of the three limiting distributions, is it Gumbel or the Frechet or the variable it belongs to. So basically this is exercise on using the three conditions I gave you. So I'll start with condition 1, right? Condition 1, all right. Before you start condition 1, you need to figure out this. But it's clear here the exponential is defined on the positive real line. So the largest point of the positive real line is plus infinity. So the upper end point must be plus infinity, right? All right. So the condition 1 says that you need to check the following. Okay. All right. Where gamma t is a positive function. Right. All right. Let's see what this is. So this is the limit as t goes to infinity of 1 minus e minus t minus x gamma t. Okay. All right, the ones cancel out. Okay. So what you have is the limit as t goes to infinity of these two cancel out, so you get this equal to the limit and this is equal to e of minus x if we take the gamma t function to be identically equal to 1. All right, hence hence condition 1 holds, right? Okay, so which means that is, it's the same as saying that is there exist two constants an and bn. An is a positive real number, bn can be any real number such that such that the limit of an x plus bn power n as n approaches infinity is equal to the Gumbel, right? All right, that's because condition 1 is satisfied, the limit must be Gumbel, right? So this is question 7. The next question is question 8. Right, question 8. Okay, here the question is to find the limit for fx equal to right. Okay, so to do this, the W of f once again must be plus infinity because the support is the positive rail line and the upper end point of the support is infinity. So let's check condition 1. Right. Now to work out this limit, we need a trick. I mean, I don't know whether you know this or not, but I will write this down. If you have something like 1 minus a to the power alpha, right, then this behaves as 1 minus alpha times a if a approaches 0. I mean, this is basically the binomial series, but only the taking account of the first term, right? The first term of the binomial series, right? So you see what I'm saying is that if a approaches 0, then 1 minus a power alpha can be written as 1 minus alpha times a. Now, you should look over here, guys. You should look at this term here and this term here. As t goes to infinity, ef minus t approaches 0. And ef minus t minus x gamma t also approaches 0. All right, hence we can use this result, right? So using this result, you get 1 minus alpha times right, the two ones cancel out and the alphas also cancel out, so you get the limit as t approaches infinity of this, right, which is equal to the limit as t approaches infinity of this, right, and this is equal to e of minus x if we choose gamma t to be identically equal to 1, right, for all t. Okay. So hence the conclusion is the same as the previous question. Right, that is there exist two constants an positive and bn real number such that the limit as n goes to infinity is equal to the Gumbel distribution, right? So this completes question 8 of sheet 1. So the question here is to find the limit, the limiting distribution right. This is the uniform distribution on the interval from 0 to 1 for which the CDF is equal to x, right? The first thing you must figure out is the upper end point. Remember, the upper end point is always the largest value of the support, which is from 0 to 1. So which in this case is clearly equal to 1. So let's check condition 1 to start with. Okay, condition 1 says that the limit this must be equal to e of minus x. And let's see what happens. So this is going to be the limit as t approaches 1 okay, and this you can write as the limit as t approaches 1 of 1 minus okay, and there's no way that the limit of this is gonna be equal to e of minus x, right? So hence condition 1 fails to hold. Okay. All right. Now let's check condition 2. Condition 2 says you need to find the limit as t approaches infinity of this, right? And according to condition 2, this must take the form x power minus alpha, where alpha is a positive number. So let's see what happens. So this is going to be the limit
Now I'm going to write this as, I'm going to divide the top and the bottom by t. So this is going to be 1 over t minus x, and this is 1 over t minus 1. Right, 1 over t, as t goes to infinity, this goes to 0, and so is this one. Right. Okay, so you get minus x divided by minus 1, which is equal to x, and this is not equal to x to the power minus alpha for alpha positive. So the conclusion is that condition condition 2 fails. Right. Also, for condition 2 to be satisfied, W of f must be infinity, which is not the case, right? Plus W of f is equal to 1 in this case, which is not equal to infinity. So hence, this is another reason why condition 2 fails to hold, right? Okay. Now let's check condition 3. Condition 3, as you may recall, is that for condition 3 to hold, W of f must be finite, which is true because 1 is a finite number, right? And also the limit as t approaches 0 of the following. Right, the following must be equal to x to the power alpha, where alpha is a positive real number. So let's see what happens. So this is the limit okay, the ones cancel out. Okay, so what you have is the limit as t approaches 0, tx divided by t, which is equal to x. Right, so this is equal to x to the power alpha when alpha is 1. So hence condition 3 holds. Right, that is, according to the extremal types theorem, that is, there exist constants an and bn such that the limit distribution, or in other words, the limit as n approaches infinity of this is equal to, because alpha is equal to 1, you have minus minus x, so it becomes x if x is less than or equal to 0, right, and 1 if x is greater than 0. So this is the viable limit when alpha is equal to 1. Okay, so this completes question 9. Now let's move on to the next question, which is the following. Find the limit for fx equal to 1 minus k divided by x to the power alpha, right, where x is greater than or equal to k. Once again, the first thing to do is to determine the upper end point. The support here is x is greater than or equal to k. So the largest point of the support must be plus infinity. All right, let's start by checking condition 1. So this is the limit okay. So this is the limit one minus k okay. This is what you get. Now the 1 cancel out. All right, so what you get is, and the k's also cancel out. So what you get is the following. You get the limit as t goes to infinity of t. This goes up divided by t plus x gamma t. Right, everything raised to alpha. Okay. Now, there's no way that the limit of this is going to be equal to EF minus x. So the conclusion is that condition 1 fails to hold. Okay. Now let's check condition 2 now. All right, let me start on a new page. So to check condition 2, first we must make sure that that w of f is infinity, which is the case in this example. All right. So this condition is satisfied. All right. So we're looking at the limit as t approaches infinity of this, and this is equal to the limit once again the 1's cancel out and the k's also cancel out. So what you have is the following: limit as t approaches infinity of t divided by tx power alpha. The t's cancel out, so the limit is going to be x power minus alpha. So hence condition 2 false. All right, that is such that the limit distribution is the Frechet. So it's the limit of this. Is the Frechet distribution, which is, I'm sure all of you know, is E and 0. Okay. Right, so this completes question 10. The next one is question 11, right? Question 11 and question 12 are something of a different kind. So let me try to first of all write down the question briefly. Okay, so consider the class of distributions with CDF and PDF given by the following. So the CDF, capital F of x, is equal to k integral from 0 to this of t power a minus 1 all right, and the PDF little f of x is as follows: k okay, where a is greater than 0, b is greater than 0, c is greater than 0, capital G is a valid CDF, right, and little g is the derivative of the capital G, all right. All right. And the question is as follows: is to show that F and G belong to the same domain of attraction. What it means is the same limits. Okay. And to show that, one of the assumptions we're going to make is that we're going to assume that the upper end point of F is the same as the upper end point of G. All right. You will get questions like this in the exam in January or February, whenever it comes. So let me show you how to do this one. All right, to answer questions like this, you need to show three different things. All right. Part A is to assume that G belongs to remember, there can be three possible limits: Gumpel, Frechet, or Weibull. So assume G belongs to the Gumpel limit, okay, and show f also belongs to the Gumbel limit. That's part A. The second part, the second thing you need to show is the following. Assume to the pressure limit and show that F also belongs to the pressure limit. That's the second part you need to show. And part C, the final part, is to show the following. Assume that G belongs to the Weibull limit, okay, and show that F also belongs to the Weibull limit. So if you can show each of these steps, right, then you will have proved that F and G belong to the same domain of attraction. So I'll start with part A, right, which is to assume that G is to assume that G belongs to Gumbel limit and show that F also belongs to Gumbel limit. Now, if G belongs to the Gumbel limit, by condition 1, there exists a function gamma t, which is positive, such that the following is true. So this is basically condition 1, which I mentioned to you earlier. All right. Now for letter use, let me call this star. All right. So I need to show that this condition holds true if G is replaced by F, right? So that's what I'm going to do. So I'm going to start with the statement that the limit of T approaches W of F of okay. Now I need to show that this is of the same type as this. Right? Now the first thing I'm going to do, I'm going to use the Lapital's rule. Now you can use the Lapital's rule because you have, as T approaches this, you have 1 minus 1 divided by 1 minus 1, which is 0 divided by 0. Right? So you should differentiate the top and the bottom with respect to T. This is what you will get. Okay. Now the two minuses cancel out, right? So you get the limit Right, in the next step, I'm gonna replace the little f here and the little f here by what is given in the question. So if you read the question, it gives an expression for little f in terms of g, right? So I'm going to replace the top and the bottom by the expression that is given in question 11. Okay, so it's going to be like this. It's going to be a long expression, so bear with me. In the top you have k, right? In the bottom you have this. Right, and multiplied by, there's one more term that I need to put, which is e times 1 plus x gamma prime at t. Okay, all right. In the next line, the next step, I'm going to group these things together, right? And also you note that the two k's cancel out; they are constants, right? And also I'm going to replace w of f by w of g, because that is an assumption of the question, right? That you can assume that the two upper endpoints are equal. So this will become the limit right. Now I'm going to put these two together, so you will get this. Okay. And I'm going to put these two together, so you get okay. And I'm going to put these two together, so you get and I'm going to put these two together. All right, and finally this term is okay. All right, now let's see what happens. You will see here that as t approaches the upper endpoint of G, because of the definition of the upper endpoint of G, this must approach 1. All right, and so is this one approaches 1, and so is this one, okay, and so is this one. Okay, so you see here that you have 1 divided by 1, which is 1, power a minus 1, also 1, and here you have c minus c, which is 0, and e of 0 is 1. All right, so a few things simplify. So you get the following. So after simplification, we get the limit as t approaches WG. Right? Now I'm going to put this and this together just for a reason that will become clear in a minute. Right? Okay, and then this one goes to 1, this one goes to 1, so the only two remaining term is this one. All right? Okay. All right, next thing is I'm going to use the next line. I'm going to use the Lapital's rule one more time, but in reverse. I will explain what I mean by reverse in a second, right? But let me write this first. Okay. Now what I mean by reverse is the following. Now if you apply the Lapital's rule to the numerator and the denominator, that is differentiate the top and the bottom with respect to t, you will get exactly what you have here. In other words, what you have inside the brackets, right? Differentiating this gives you this times this, and differentiating this gives you this for the minus, and you'll also have minus minus, which will cancel out, right? So I applied the Lapital's rule from this line to this line, so going from this step to this step, so backwards. So that's what I meant by reverse. Okay. All right. Now these two terms are the same, so you can combine them. So this becomes the limit as t approaches w of g of to the power b, right? Okay, in the next step, I'm going to use star, which is the assumption that I made in the previous slide. So according to that, the limit of what is inside the brackets is equal to this. All right, so this is equal to this. And this is of the same type as this, because p is a positive number, right? So hence we have shown that f that f also belongs to the Gumpel limit. Part B. So I'm going to assume that G belongs to the Fresher limit. All right, which means the following. It means that the limit as t approaches infinity of right. Now what we need to show is that this is true, if G is replaced by f. Right? So that's what I'm going to do. So I'm going to start with the statement where G is replaced by f. Right, and I'm going to show that this is of the same type as this. All right, the first step, I'm going to use the Lapital's rule. All right, you can use the Lapital's rule because when you have t goes to infinity, you have 1 minus 1 divided by 1 minus 1, 0 divided by 0. Okay, so this is the limit if you differentiate this with respect to t, you get x okay, and the two minus signs cancel out, so you have the limit as t goes to infinity of okay, and in the next line I'm going to replace f by the expression given in the question, right? So this is going to be the limit the expression given in the question is the following. Right, and in the bottom you have k okay. Right, now you see that these two cancel out. Now I'm going to group these together, so you have the limit so grouping these two together, you have the following. Okay, grouping these two, you have this power b minus 1, and grouping these two, you have e Okay. Right, now as t goes to infinity, by definition, each of these guys will go to 1, right? Because infinity is the upper end point. Okay. And this guy here will also go to 1, and so is this one will also go to 1. Okay. So you see a lot of things simplify. You have 1 divided by 1, which is 1, c minus c, which is 0. Right. All right, so this becomes the limit as t approaches infinity of x gtx gt. Okay, let me group this as 1, and then you have this term here, which is 1 minus all right, before I go further, let me go back and let me call this equation double star. Okay, I will need it later. Okay, all right, now back to this. All right, in the next step I'm going to use the Lapital's rule one more time, but in reverse. Right, the same as before. But, all right, so you get limit as t approaches infinity of 1 minus right. Okay, what I meant by reverse is the following, that if you differentiate this with respect to t and this with respect to t, you will get precisely what you have here and here. All right, so that's Lapital's rule applied in this direction, right, in reverse. All right, now these two terms are the same, so you can group them together. So you have the limit to the power b, right? Okay, now in the next line, I'm going to use double star, which is the assumption that I made at the beginning. So using double star, the limit of this is x to the power minus alpha power b, all right, which is x to the power minus b alpha. B is a positive number, so this is of the same type as x power minus alpha, right? So hence we have shown, hence f also belongs to the Fresher type. Of Fresher limit, okay? All right, so we have shown part A, we have shown part B. So the only remaining part we need to show now is part C, all right? So let's try to do that. So part C is, so I'm going to assume that G belongs to the Weibull limit right, which is the same as saying that the limit as t approaches 0 of the following is equal to x to the power alpha, where alpha is a positive number. Alright, for later use, let me call this triple star. Okay. Alright, now I'm going to show that this statement here is true if G is replaced by F. Alright. Alright, so so this is what I'm going to look at, right? So, well, this should be F, guys, not G. Okay. Now, in the first line, or first step, I'm going to replace the W of F by W of G because we are assuming, as I said before, that the two are equal. So this is the same as the limit as t approaches 0 of Alright, that's the first step. In the second step, I'm going to use the Lapital's rule. So the differentiate, you can do that because this is basically 0 divided by 0, 1 minus 1 divided by 1 minus 1, right? So this is going to be the limit as t approaches 0 of the following. You have x okay, and in the next line I'm going to replace the little f's, this one and this one, by the expressions given to us in the question. Okay, so this is going to be capital K to the power a minus 1 right. Then in the bottom you have this capital K right, and the remaining term I'm going to write it over here. So it's E Okay. All right. Okay. Now you see that the two k's cancel out. This one and this cancel out. All right. All right. In the next line, I'm going to group the things together. Right. So it's going to be like this. It's going to be the limit as t approaches 0. Grouping these two together, you have this. All right, grouping these two together, you have this. Okay, grouping these two, you get this. And finally, grouping these two, you get this. All right, now let's take the limits. As t goes to 0, by definition, this, right, is going to go to 1 by definition of WG. And this will also go to 1. This will also go to 1. And so is this one. Will also go to 1. All right, so a lot of things simplify. You have 1 divided by 1, and you have c minus c. All right, so you have, after cancelling out those terms, this is what you will get. You get the limit t approaches 0 of x times right, that's these two terms, right? And then you have this term here, which is okay, right, okay. Now, as before, in this step, I'm going to use the Lapital's rule in reverse. All right, so what it means is the following. It means the limit, this all right, so when you should differentiate this and this with respect to t, you will get precisely what you have here and here. So it's the application of Lapital's rule from this step to this step. Okay. Now these two terms are the same, so combining them, you will get this. All right, and now I'm going to use the assumption, which is triple star. So according to the triple star, the limit of this is equal to x to the power alpha power b, right? So this is x power b alpha, which is of the same type, right, because b is positive, right? Hence, we have shown that f right, we have shown that f also belongs to the Weibull limit, right? So to conclude, we have shown that f and g belong to the same domain of attraction. This completes question 11. Okay, next I will do question 12, which is a similar question, right? So this is question 12. So okay, so you have a class of distributions with the CDF capital F of x given by the following. Right, and the PDF given by little f of x, which is equal to the following. where the following is true. So where A is positive, B is positive, beta is positive, G is a valid CDF, right, and little g is the derivative of capital G. Okay, and the question is the same, that is, show that F and okay, and once again I'm going to assume that the upper end point of F and the upper end point of G are equal. All right, as in the previous question, we need to show three things. Right, part A is to show that assume G belongs to the Gumbel limit, okay, and show that F also belongs to the Gumbel limit. So this is part A. Part B is to assume that G belongs to the pressure limit, and show F also belongs to the pressure limit. And finally, part C is to show that assume that G belongs to the Weibel limit and show that F also belongs to the Weibel limit. All right, so we need to show each of these parts as it was the case with question 11, right? By the way, in these two terms are the beta function, there is a video about the beta function on the course website, so you may want to have a look at what these actually mean, right? Okay. All right, so let's start with part A. All right. So I'm going to assume G so which means that there exists a function gamma t which is positive such that the following is true, that the limit as t approaches right. All right, let me call this, for later use, let me call this star. Okay? Now what we need to show that this statement is true if G is replaced by F. Right? Okay, so as t approaches the upper end point of f, you have 1 minus 1 divided by 1 minus 1. So the natural thing to do is to use the Lapital's rule, right? So you get the following: minus all right, the two minus signs cancel out, so you have the following: right. Okay, next I'm going to replace the two little f's by the formula in the question, right? So if you look at question 12, which is this one, so this expresses f in terms of g, right? So that's what I'm gonna do now. So it's gonna be a little clumsy. So right, that's this one, then this divided by okay, that's at the top, and the bottom you have this. Okay, and this multiplied by this term, so I'm going to put this up here, 1 plus x, right. All right, you see you will see that the beta A, power A, cancels with this, and you will also see this guy here cancelling out with this. All right, now the next thing I'm going to do, I'm going to group this guy with this, this with this, this with this, and this with this. All right, so that's what I will do in the next step. And also I'm going to replace the W of F, because they are equal. So I'm going to replace this with W of G. All right. Okay, now let's do the grouping. Group these two together, you get this, right? Group these two, you get and group these two, you get this. And group these two, you get this. And then this term here. Okay, all right. Now you will see a few things simplifying. As t goes to the upper end point of G, by definition, this has to go to 1. All right, this goes to 1. And this goes to 1, and this also goes to 1. Okay, so 1 divided by 1 is 1. Here you have 1 minus beta, which is beta, and the same thing here, 1 minus beta is beta. Beta divided by beta is 1. Okay, so a few things simplify. So you have the following. You have the limit, right? Of this, right? You have this term here. I'm going to combine these two for a reason, you will know. All right, these two terms cancel out, right? So the only remaining term is this one. Okay, here we go. All right. In the next line, I'm going to apply the Lapital's rule in reverse. I hope you know by now what I mean by that. So Okay, so I'm applying, if you differentiate this and this with respect to t, you will get precisely what you have here and here, right? So it's the Lapital's rule applied in this direction from this step to this step. All right, so now these two are the same, so you can combine them together. So you get limit to the power b, right? Okay, now I'm going to apply the assumption which I called star, you may recall. So according to star, the limit of this is e of minus x, right? So this is equal to e of minus bx. B is a positive number, so this is of the same type as e of minus x. So hence we have shown that f also belongs to the Gumbel limit. Right? Okay. So we have proved the first part, part A. Next, we're going to do part B. So for part B, all right, I'm going to assume that G belongs to the pressure limit. Right? So which is the same as saying that the limit as t approaches infinity of this is equal to x to the power minus alpha, where alpha must be a positive number. Now we need to show that this statement is also true if G is replaced by F. All right, so we need to show this. The limit as t goes to infinity of right, so that this is also equal to of something of this type, right? So in the first line, because you have 1 minus 1 divided by 1 minus 1, you can apply the Lapital's rule. All right, the two minus signs cancel out, so you have the limit Okay, now I'm going to replace the two little f's by the expressions given in the question. So it's x times, the expression for this is going to be right? Okay, and in the bottom you have something like this. All right. So two things cancel. This guy here cancels with this one. This guy cancels with this one. All right. In the next line, I'm going to group this with this, this with this, this with this, and this with this. All right. So you have the following. Okay, these two grouped, or these two together gives you all right, and these two together gives you right, and these two together gives you all right. Okay, now as t goes to infinity, this goes to 1, right, and this one also goes to 1, this one goes to 1, and so is this one. All right, so you have 1 divided by 1, and here you have beta divided by beta. All right, so the only terms remaining are this term and this term. All right, and in the next step, you will know what I want to do by now. I'm going to apply the Lapital's rule in reverse. Right, for this term. So you will get you will get this multiplied by this, right? So I differentiated this. You should differentiate this with respect to t, this with respect to t. You get precisely what you have here. These two are the same, so you can combine them together. So you get the limit right. Now before I go ahead, let me let me go back to the assumption, which is this one I made, and let me call this equation double star. Right? Okay, now returning to this, using double star, all right, the limit of this is x to the power minus alpha power b, so which is x power minus b alpha. Because b is positive, this is of the same all right. So hence we have shown that f also belongs to the pressure type or pressure limit. All right. So we have proved part A and we have proved part B. So the only remaining part to prove is part C. So let's assume that G belongs to the viable limit, right? Which is the same as saying that the limit is equal to x to the power alpha, where alpha is a positive number. Now we need to show the following. We need to show that the limit the limit of this is also of this type. Right. Now as t approaches 0, you have 1 minus 1 divided by 1 minus 1, so you can use the Lapital's rule, and if you do that, this is what you will get. Now, before I proceed, I'm going to replace the W of F by W of G, because that's an assumption of the question, right? All right, okay, in the next step, I'm going to replace the two little f's by the expression given in the question. So you have the following. So this is going to be x times put this in the numerator, and in the denominator you have excuse me, there's no x here, it shouldn't be. Excuse me. So it should be just this close bracket power a plus b. All right, you see again that the beta a cancels with this one and the beta function cancels with this one. All right, in the next line I'm going to group the things together, so you'll get the following. So grouping these two, you get x you get this, right? And grouping these two, you will get the following. Grouping these two, you get this. And finally, grouping this one and this one, you will get the following. Okay. All right. Now, as t approaches 0, by definition, this approaches 1. By the definition of upper endpoint of G, this approaches 1, and this also approaches 1. This also approaches 1. And this also approaches 1. All right, I left out a bracket here. Okay, so you see 1 divided by 1 is 1, and here also beta divided by beta is 1. So the only terms that remain are this term and this term, right? So let me write them down. So it's the limit Okay. All right. Okay, and in the next step, I'm going to use the Lapital's rule in reverse. Right? So what I mean by this is the following. So I'm using the LH rule in reverse. All right, so if you differentiate this and this with respect to t, you will get what you have here and here. All right. Okay. Right, now these two terms are the same, so you can group them together. So you get limit as t goes to 0 of to the power b. Right, now before I go ahead, let me go back to the assumption for part C, which is this one. Right, and let me call this equation triple star. Okay. So this is the assumption that we made. So using triple star, so I'm going to use triple star in this line. The limit of this is x power alpha power b. So this is x power b alpha, which is of the same type as x power alpha, because b is positive. All right, so hence we have shown f also belongs to the viable limit all right. So just to conclude this question number 12, we have shown that f and g belong to the same domain. Okay, the same domain of attraction. Right, so this completes question number 12. Now there are many other questions of this kind, that is, namely question 11 and question 12. There are many other questions of this kind in the course website with full solutions. So I suggest that you try to do those questions without looking at the solutions. And if you get stuck, you can look at the solutions. Every past exam paper contains a question similar to question 11 and question 12. So please try to do them by yourself. Okay. Okay. The next question on sheet number 1 is question 13, right? So question 13 is asking you, right, this is question 13. It's giving you the CDF of the GEV distribution, which I'm sure all of you know. And the question is to find these, find the inverse function of the, is to find the inverse function of the CDF. Alright, so to find, I'm sure all of you know how to find an inverse function. You set g of x equal to p and solve for x in terms of p. Alright, so this is equal to p. Taking the logs both sides, you get minus alright. Bringing the minus in, up to the right hand side, and you get this. Alright, and then this, and finally taking all these constants to the right hand side, you have x equal to the following: sigma by, sorry, I left out sigma by psi of this minus 1, then plus mu. So this is the solution for x. So hence we have shown the inverse function of g at p is equal to okay. So this completes question 13.